to Decaf-Math. So I thought that we could work through a problem together. This is a random problem from Linear Algebra. So let's find any eigenvalues, if there are any, and eigenvectors. Of this matrix 2, 4, -1, 6. Okay, so find eigenvalues and eigenvectors of this matrix. So remember that an eigenvalue and eigenvectors will satisfy this equation. So the idea is that if we multiply this matrix by a vector, then it's the same as multiplying by a scalar. So that's the eigenvalue, this lambda, that's lambda, times x, lambda times that vector. So the idea is that we're only scaling the transformation made by this matrix is only scaling the vector by a scalar. That's the idea. We haven't really talked about this in depth or anything on this channel yet, but I just wanted to work through this example in case any of you are studying linear algebra. I know that there are at least a few. So when we rearrange this, really we need to find the characteristic polynomial. And we'll get that by finding the determinant of lambda I minus a, and setting that equals 0. So I being the identity matrix, that is the matrix where we have 1 along the diagonal of the matrix and zeros everywhere else. So, 1, this would be the 3 by 3 identity matrix, but it goes on and on as you need it to. So the I is going to be based on the size of your matrix A. So in this case, this is our 2 by 2 matrix. So our I only needs to be I2, which is just going to look like 1, 0, 0, 1, with the 1s in the diagonal and zeros everywhere else. Okay, so the characteristic polynomial is going to give us the polynomial that we're going to solve to find lambda, to find our eigenvalue or eigenvalues. So we just need to figure out what this matrix is, just using lambda I, just using this formula in our matrix, and then find the determinant of that. So let's just do this in pieces. Lambda I is lambda I minus a is going to be lambda times my identity matrix for 2. So in this case, we're going to do I2 because A is two rows and 2 columns. So that means that, remember, when we're subtracting and adding matrices, they have to be of the same size so that we can find corresponding values. So here we're going to do lambda times 1, 0, 0, 1 minus a 2, 4, negative 1, 6. And then when we multiply by a scalar, we're going to get lambda 0, 0, lambda minus 2, 4, negative 1, 6. And that's typical. The lambda I is basically, if you practice this a lot, you'll get used to seeing lambda down the diagonal here and zeros everywhere else, because it's just going to be lambda times the ones, right? Then when we subtract like we normally would with matrices. Lambda minus 2, 0, minus 4 is negative 4. 0 minus 1 is positive 1. Lambda minus 6, like that. Okay, so this is our lambda I minus a. And so in this case, I guess I'll put the I2 just to make it clear. We're talking about the 2 by 2 identity matrix. So now we just need to find this, the determinant of this. So we just did lambda I2 minus a right here. And we got this. So we just find the determinant of this thing and set that equal to 0. And that'll give us the characteristic polynomial that we'll solve. So the determinant of this this is another way to write the determinant, is with the straight lines like this. And if you can remember how to find determinants, we can review it here too if you want, but determinants are, for a 2 by 2 is just this diagonal, so this times this minus this times this. So let's see if I can draw that out. So it's these two multiplied together minus these two multiplied together. So that would be lambda minus 2 times lambda minus 6 minus negative 4, because negative 4 times 1. I'll just write it out. Okay, so we can distribute as normal, FOIL. So lambda first, outer, inner, last, right? So lambda squared minus, that's going to be outer is negative 6 lambda, inner is minus 2 lambda, so that'll be minus 8 lambda plus 12, negative 2 times negative 6. And then we have a minus 4, so plus 4, which is lambda squared minus 8 lambda plus 16. So now we set this determinant to equal 0. So that's our characteristic polynomial. And now we solve this for lambda, and that'll give us any eigenvalues. So in this case, if we solve it, we can factor this into lambda minus 4 squared equals 0. So in this case, we only have lambda minus 4 equals 0, which is just lambda equals 4. So we have one eigenvalue. Okay, so eigenvalue. And remember, since we're trying to solve this equation, a times my matrix A times my vector equals my lambda times x, we are going to have a corresponding eigenvector. And so that's what the question is. So we have lambda equals 4, so that's good. And now to find eigenvectors, we kind of need to go back to this lambda I2 minus a thing, and we can just plug our specific eigenvector in. So you might sometimes get like multiple ones, like this characteristic polynomial might be really complicated, or you might factor into, you might get 2 eigenvalues, for example, and you have to find the eigenvectors that correspond to each, but it doesn't matter, you can just repeat this idea. But for lambda equals 4. So this is what I do. It's like for each eigenvalue, I find the corresponding vector. So what I'll do is, there are a few ways to do this actually, but I'll go back to my lambda I2 minus A and just go ahead. So that was this matrix, lambda minus 2, negative 4, 1, and lambda minus 6. And I will go ahead and plug 4 into my lambda here. So I would get 4 minus 2 is 2, negative 4, 1, and then 4 is negative 2. So what I just did here is basically found the lambda I2 minus A. And what that does is basically, remember that we're trying to find AX equals lambda X. So what we did here was we found lambda I2 minus A, and since we already did the general calculation here in terms of lambda, now that we have a characteristic polynomial 4, I just plugged that in. But really, this lambda I2 minus A comes from rearranging our definition of an eigenvalue and eigenvector. And we didn't do the full proof here today, but we can in the future. But you can kind of start getting the intuition here where you're rearranging this equation, moving the AX over here, and lambda X is the same as lambda I X, and then pulling out your vector X. But the important thing is that you're solving for some vector X, because X is our eigenvector. And we want that to equal 0. So, in other words, this would be this definition here, where lambda is our eigenvalue and x is our eigenvector, is equivalent to trying to solve for lambda I2 minus A, or I anything, but in this case 2, because A is 2 by 2. But this matrix times x equals 0. And so we just found what lambda I2 minus A is. It's this. So I'm basically trying to solve or find any vectors where this times that vector equals 0. So I'm going to let my vector x have, x1, x2 have coordinates of x1 and x2. And you can always write it like this, because like x1 and x2, because all this stuff only works for square matrices. So it has to be n by n, in this case 2 by 2. But you won't ever have weird situations where things don't line up. So just make your vectors the same dimension as the matrix A. Okay? So we're just going to try to solve this and find what x1, x2 is. So these are going to be like the coordinates of our vector x, which is going to be our eigenvector. At this point, this is where I would say that there are a few ways to actually solve this. You can make a giant matrix and row reduce or whatnot, but since this is a linear case, I'll write it out just to avoid confusion. So when we multiply this, we're doing 2 times x1 minus 4 times x2. So remember, I guess I should have been more clear, this is actually a 0 vector. So this would be 0, 0. Okay, so this times x1 minus 4 times x2, and then the next entry would be 1 times x1, and then minus 2x2. Okay, so it's just normal matrix multiplication, and that's why it's important to be really clear with how to work with matrices before you get into all of this, but that needs to equal 0. So we're just solving simultaneous, like this part equals 0, this part equals 0. So we're solving two equations with two variables. 2x2 equals 0. Okay, so at this point, this is where I said you could do row reduction if you want to set this and solve this with Gaussian elimination or something like that. But here you could pretty much see that if you multiply the second equation by 2, so 2x1 minus 4x2, it equals 0. Or you can actually you could have divided the first equation by 2 on both sides, and you'll still get x1 minus 2x2 equals 0. So basically, these two are the same equation, equivalent equation, which is totally fine, and that's actually what we would expect. So basically, this gives us the relationship between x1 and x2. And so you'll just take one of them, and I'm going to take this one since it's the simplified form. And you get that x1 equals 2x2. Which means if I try to make a vector out of this, where x is my x1, x2, if I let x2 equal t, then x1 equals 2t. Just like make it parameterized. So then I would get x1, x2 is 2t and t, where t is just some constant. And so then I can pull the t out here, and I would get to 1. And that is my eigenvector. 2, 1 would be my eigenvector, corresponding to lambda equals 4. The t here is some constant, it's a scalar, and so that's why I can pull it out and just kind of ignore it. Technically, I guess you could include any multiple of 2 1s. So at this point, you can find any multiple. I just took this 2 1 as an example, and that's why I boxed that. But really, all vectors of this form are eigenvalues associated with lambda equals 4. So notice that there's going to be an infinitely many, and as long as t is a scalar and x1 and x2 are related in this way, we have an eigenvector. So there will be infinitely many. So t doesn't actually have to be 1. But this is the 2 by 2 case. So sometimes you'll get, like in 3 by 3 cases, you'll get like, s times, you'll get two parameters here that you'll need to put in. And so you'll get something like s times, something, like, I don't know, 102 plus t times -1, I don't know, 0, 1 or something like that. And so you'll get two parameters, and in this case that would be infinitely many eigenvectors as well, of course, because s and t can be any constants. But you can also think of the entire eigenspace being spanned by two matrices here, two vectors here. So the whole space would be spanned by these two vectors. But we can do a 3 by 3 case later on. I haven't really made any videos yet on finding determinants, and so I just wanted to jump into this as an example for anyone who's in linear algebra now without, rabbit holing into a whole bunch of math concepts. But I hope that this was still kind of relaxing and fun to see all this math written out. And I definitely suggest that if you are doing more than 2 by 2s here, that you review row reduction, because this solving two equations with two variables isn't so bad. But when you get to the 3 by 3 case, you can set, for instance, you set your coefficients in 2, -4, let's say we have another 1, and you put the zeros in like this, and, you know, all of your coefficients, and then you do your row reductions. You try to solve in this way with 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay? And so that would be like, you know, something like taking a step where you do, you know, R1 minus 2, R2, that kind of stuff. Okay? Alright, so I hope that this was relaxing, and just I'm trying to keep it kind of simple and clear and make my videos in kind of small chunks. This was a nice little review for me as well, and I hope that you're having a really, really great day or night or evening, and it's been really great getting to know you all, and if you're new here, welcome. It'd be awesome to have you join, and the more feedback that I get, the more that I have a sense of what everyone is learning and what you're interested in, and as usual, I'll just be jumping around between topics just based on what I feel inspired by. Okay, I will see you around. Bye.